All right, everybody. So this is going to be my first video for the second exam. And this is going to be going over Chapter 8, which is metabolism. It's a word that you've probably heard quite a bit. You've probably heard people talk about like, oh, you just have such good metabolism, which hopefully we all have good metabolism. So we're just going to start by breaking that word down, learning what it means. Metabolism just refers to the chemical reactions of biological systems. One biological system that is very near and dear to all of us is the human body. So it's going to be the sum of the chemical reactions of biological systems. Let me sort of just include that it is the sum of. It's pretty important. So it's every chemical reaction that's happening in your body makes up your metabolism. So when we say chemical reactions, we specifically mean these reactions, they are all going to be converting matter and energy in your cells. So maybe that's breaking down ATP for energy. Maybe that is, synthesizing proteins out of amino acids and changing these things. Now, these metabolic pathways is what we're going to call them. They're really split into two pathways. And it's also, we're going to get more into it at the end of the video, but enzymes are required for metabolism. If we didn't have enzymes, we wouldn't work too well. Life would be pretty tough. Not possible, actually. But they require enzymes, which are biological catalysts. We're going to get to that later, though. So right now, I want to talk about these two pathways. So I'm going to try to uncover it a little bit at a time as we go through. So we have two types of pathways in metabolism. We have catabolic and anabolic. So I'm just going to go ahead and define those real quick. Catabolic pathways always are going to involve breaking down molecules. So when we break down a molecule, very simply, we just have AB is going to transform into A plus B plus energy. This is really important. Catabolic pathways release energy. So the most known catabolic pathway, at least the one you're going to be familiar with, is cellular respiration. So the reason cellular respiration is a catabolic pathway is because, as we will learn in the next chapter, if you don't already know, spoiler, we're breaking down glucose into energy. We're converting it into energy that our cells can use. So that's catabolic. It's breaking down molecules, cover a little more, and it releases energy. I say creates energy. That's not correct. You can't create energy. It releases energy. Better way to put that. Anabolic is going to be just the opposite. Anabolic is going to be building up molecules. So an anabolic pathway would be protein synthesis. We're starting with a bunch of amino acids and we're linking them together to form a larger molecule. So instead of AB breaking down to A plus B plus energy, anabolic is just the opposite. It's A plus B plus energy yielding AB, the synthesized molecule. Always, anabolic is going to require the input of energy. And if you forget, I always try to think anabolic steroids is something that, you've probably heard of. Whole bunch of people have used them or claim to not use them while using them. But anabolic steroids are going to be what builds up muscles, right? You take the anabolic steroids and you get jacked. This is supposed to be a little arm with a big bicep, but I can't draw. So that's very basically catabolic, anabolic. We're going to come back to that chart and fill it off as we go. So, metabolism, we're still going with it. We're going to define a few key terms that you've heard before, but you need to know exactly what they mean. Energy means the ability to do work. Energy, you can think of like if you're like, oh, you're high energy right now. You're you have a lot of energy right now. You could go for a run. You have the energy. You could go run. You could go lift weights. You have high energy. But if you're like, oh, you're really low energy, you're not going to be going for any runs. I guess you could, but you'd do it way better if you were high energy. So energy is the ability to do work. Work is actually transferring energy over a distance. So when you think of work, think of labor, right? We're moving things, you know? For some reason in my head, I think of lifting weights. You're putting in work. You're moving the barbell or the dumbbell or whatever you're doing. Or it could also be moving your body if you're going for a run, if that's your thing. I don't really do cardio. I should probably do more of that. But so that's work, is the actual transfer of energy. Chemical energy refers to potential energy of bonds. So chemical energy is potential energy. Those are synonymous in biological systems. Don't tell the physicists that I said that. Potential energy is just like it sounds. It is the energy like you could have. It's not actually being enacted like kinetic energy. But we need to talk about bond strength because this is not super intuitive, unfortunately. So here I have two bonds. I have an OH bond and I have a CH bond. We know this OH bond is very polar, and we know the CH bond is very nonpolar. So I drew the shared electrons here. You can see that these shared electrons are hanging out near oxygen because it's high electronegativity, creating a partial negative charge right here. And then there's a partial positive charge over here. But these ones are sharing these electrons equally. Intuitively, you kind of want to say the stronger bond probably holds more energy. And that, unfortunately, is not true. Stronger bond is lower potential energy. Weaker bond, like a nonpolar bond, is going to be higher potential energy. If you ever forget that on a very basic level, think of fats, think of lipids. We know that lipids are composed of a bunch of hydrocarbon chains, CH, 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 CH. That's what makes lipids. And those are energy molecules, right? They store energy because these bonds are nonpolar. To quickly sort of go into why that is, we're not going to worry about it too much. But the more stable that a bond is, the less potential energy it has. And this is because you don't actually ever release energy by breaking bonds, which kind of goes, unfortunately, against what we said about catabolic pathways, because we said catabolic pathways is the breakdown of molecules to release energy. So, Ben, what are you talking about? Well, it's not that easy. And if you think about it, it makes a little sense, but just stay with me. I can't just make this oxygen and this hydrogen split apart. I can't do it. I have to physically snap them, right? I have to go in and I have to break it. But that is requiring energy. Me taking this pen, let's pretend that there are two molecules on the end of my pen. When I actually go to snap it, that takes energy from me. The same is true for this carbon-hydrogen bond. The key is it's a lot easier for me to break this bond than it is to break this bond. This is strong. These don't want to separate. This oxygen wants these electrons close to it. This hydrogen is happy giving it those electrons. Whereas the CH bond, they're kind of just, whatever. If you break me, you break me. If you don't, whatever. So it's weaker. It's easier for me to break this bond than this bond. This one just snaps. So the reason that we say these are higher energy is because it takes less energy to break. So why do catabolic pathways, which break down things, release energy? This is because breaking weak bonds, like this OH bond, to form stronger bonds, or I apologize, I said that incorrectly. Breaking weak bonds, like this carbon-hydrogen bond, breaking this bond in order to form stronger bonds releases energy, because forming bonds releases energy. So if I break this CH bond, and it's really easy to break, it's going to take a little bit of energy. But then if this H combines with an oxygen, when this bond forms, it releases this much energy. So we've sort of just gotten this much energy. All I really want you to know is nonpolar bonds are higher potential energy. Strong bonds, like ionic bonds, are low potential energy. Write it down on your note sheets because that's super easy to forget. You don't necessarily need to know the chemistry of it. It helps. Maybe it helps you, maybe it doesn't. But that's why. And to sort of explain this further, I have drawn out here ATP hydrolysis. So we all know ATP is the energy molecule. Hydrolysis, the word hydrolysis, we hear hydro, which is water, and lysis. Lysis means to cut. So hydrolysis means to cut using water. So this is sort of how ATP gives us energy. We combine ATP with water, and we get out ADP, and we get HPO4. There are charges. I don't care about the charges. That you can let Dr. Shigley worry about those. So just to draw this out, though, to sort of represent the whole breaking weak bonds to form strong bonds. So here we have this OH, right? We have the ATP. We have phosphate 1, phosphate 2, phosphate 3. These have negative charges, right? So this phosphate right here in this dashed line has a negative charge, and this third one has a negative charge. Two negative charges want to repel each other. They don't want, it's hard to stick them together. It's hard to stick two magnets together on their negative end. So they aren't strongly bonded because their charges are like. So they want to repel. So when water comes along and sees this weak bond here between these phosphates, it's going to go, oh, okay, I'm going to stick an H on this O, and that's going to release this P and these 3 oxygens, and I'm going to stick an OH group on that P. So that ends up looking like this. You see, at the end of this second phosphate, we have stuck this hydrogen, and then we've taken this OH and stuck it here. OH, as we said up here, is a strong bond. So we have formed these strong bonds, and forming a strong bond releases a lot of energy. But breaking these weak bonds was easy. It was easy to go in and snap these phosphates apart. It's like a twig. It's nothing. So water does that and then forms these strong bonds, and that releases energy. Big takeaway from this page that I want you to know is this box up here. Know those 3 definitions, and know that nonpolar is high potential energy. Polar is low potential energy. So that's it for that page. On to the next one. I'm chugging along here. All right, this is a wordy page. It's going to be a lot of definitions. I'm going to go through these kind of quick. Feel free to pause, read. Entropy, which is going to be represented by S, is a measure of disorder in the universe. The universe always wants to move to increased entropy, to more disorder. If we want to keep order and maintain order, you got to put energy in. I think of your room. It's easy to get your room dirty. You know, you throw clothes everywhere, you leave food out, right? And your room gets dirty. To clean your room and get it orderly, you have to put in the work, or, well, the energy in this case. So entropy is a measure of disorder. The universe and every system in it, including the human body, naturally moves to increase entropy or disorder. But we have to maintain order using energy. So sort of based on this entropy, we have 2 kinds of reactions. We have spontaneous reactions and non-spontaneous reactions. Spontaneous reactions just happen. You don't have to put any energy in at all. They will happen naturally if the reactants are there. For example, if I have, let's say I have an H plus and an O minus. This is a bad example, but just well, it'll be 2 minus and an O2 minus. This positive charge and this negative charge, they want to come together naturally. They want to do it. So they're gonna form OH minus. That's spontaneous. I didn't have to push those together. They just do that on themselves. However, non-spontaneous requires us to input energy, and it decreases the entropy of the universe, so it creates more order, whereas these spontaneous reactions increase entropy by releasing energy. So spontaneous releases energy, doesn't require it though. Non-spontaneous, we have to put energy in. If I take that same OH minus and I want to rip it back apart into O2 minus and H plus, I've got to grab them and I've got to pull pretty hard to get those apart because those charges want to be together. So spontaneous, no energy requirement. Spontaneous, or non-spontaneous rather, requires energy. Remember these. These are very, very important. So this is the second law of thermodynamics. And basically, you can just think of the second law of thermodynamics as entropy always increases naturally. Let's include naturally. That's a good word to add there. So entropy always increases naturally in every system, in the universe as a whole. It's always increasing. So that's the second law. What about the first law? You've all heard it. Its energy cannot be created or destroyed, just converted. I can't make energy. I can't destroy energy. I can take my glucose molecule and I can break it apart a bunch and use that to get energy. Or I can burn a piece of paper. That energy that was in the molecules of my piece of paper when I burn this, the energy is just going to be given off as heat energy, right? So that's the first law. All right, next topic, we have this triangle G. Triangle means delta. It's a Greek letter, and it always means change. So we have the change in G, or delta G. Delta G refers to Gibbs free energy. Gibbs free energy is the amount of energy gained or lost by the system in a reaction. And you see I capitalized system. It's because when we get to talking about positive and negative values, you need to remember that I am talking about the system. So what I mean by that, if I'm breaking down a glucose molecule, catabolic pathway, if I'm breaking that down, I'm releasing energy. But releasing energy means energy is leaving the system. So if delta G is a negative value, that means that the products have less energy in their bonds than the reactants do. Another way to think about this is that the products are also going to have a plus energy, but that energy is going to leave the system. So negative delta G is always going to be energy being released. And that's kind of hard to remember because you kind of want to say, yeah, positive, that means energy. No, negative delta G, energy is released. So where does the energy go, though? Out of the system to be used. Maybe you break down that glucose and then you use the ATP to contract your muscles. That energy left the system to be used to contract your muscles. So if delta G is positive on the flip side, it means that the products have more energy in their bonds than the reactants. So if I have A plus B yields AB, there's more energy over here and less energy over here. I had to get that energy from somewhere, though. So that means that energy is going to be in the reactants. I have to put energy in. Think of photosynthesis. I have to build this glucose molecule now. I have to push all these pieces together. Takes energy. So negative delta G, remember, which was the release of energy, is exergonic, is what we call that. Exergonic means energy exits the system. Try to remember, exits, energy exiting the system. Positive delta G, we call that endergonic. We have to put energy into the system. That one was tougher. I had to think of something, though. But endergonic is a positive delta G, meaning energy has to be put in on the reactants. Exergonic is a negative delta G and means that we have energy in our products. So how do these relate to spontaneous and non-spontaneous? If you remember, I said non-spontaneous requires the input of energy, which means positive delta G, whereas spontaneous did not require me. I did not need to put energy in, so spontaneous is always negative delta G. So we do have this equation. This is one way to think about the equation, but this is the one I want you to know. Delta G, which is Gibbs free energy, which is the amount of energy gained or lost by the system, equals delta H, which is enthalpy, which is essentially a measure of potential energy. This would be given to you. Keep in mind, though, this is delta H. It's the change. So let's say that my products have 1,000 joules and my reactants only had 100 joules. This delta H is the change. So I gained 900 joules, so this would be 900. Just remember that this is change. So anyway, it's delta H, which is the change in enthalpy, minus the temperature in Kelvin, which we will give it to you in Kelvin, times delta S, which is the entropy. Remember entropy, measure of disorder? There it is again. We would give you this value as well. We would give you delta S. Or maybe we would give you starting and ending entropy. So if we're ever looking for the change, you always do end minus beginning. So you would do final entropy minus starting entropy. So I said we would come back to our catabolic and anabolic thing, and this is going to be ultimately what really matters, I think, on the exam. So remember, we said we have breakdown molecules, catabolic, build molecules, anabolic. We put energy into the anabolic pathway. We had to add energy to the system. In the catabolic, though, we got energy out. That's a product. So that means that catabolic pathways are spontaneous. Anabolic pathways are non-spontaneous. We also know that catabolic pathways are going to increase the entropy or disorder of the universe or the system. And we know anabolic pathways are going to decrease entropy or disorder of the system. So this is going to make it more orderly, kind of like we're building things, we're ordering it. Catabolic is going to create disorder. It's going to make things a mess. We're going to have ATP all over the place. It's going to be a problem. It's not. You need that energy. We also now know that catabolic pathways, since they are releasing energy, are going to have a negative delta G and be exergonic, whereas anabolic will have a positive delta G and be endergonic. So that's it for the catabolic and anabolic pathways. This is all great information. This would be really good to have on your note sheet in some form. Write that down. Leave it up there a minute, pause it. Okay, that was a lot of words. Know this equation. Know spontaneous and non-spontaneous really well. Know your first two laws of thermodynamics and be able to use this equation. All right, we're on the last topic for chapter 8, so hopefully we'll get this done in half an hour. Enzymes, I mentioned them at the beginning. Metabolism requires enzymes. What is an enzyme? It's a biological catalyst. What is a catalyst? Catalyst is anything that speeds up reactions by lowering activation energy. We'll get to that in a second, though. Enzymes are also proteins. Proteins. Enzymes are always proteins that speed up chemical reactions, very importantly, without being used up or consumed. That means the same enzyme can be used over and over and over and over again. Let's say we have a kinase. Kinase is a word that you'll get very familiar with. Kinases phosphorylate things. They give things phosphates. So I can use that same kinase to just keep phosphorylating multiple different things. So I don't have to necessarily include it in a chemical equation. Let me adjust my camera here just a little bit. I think you can see everything. Awesome. All right, sorry. So let's talk about this speed up reactions by lowering activation energy. So I'm going to give you 4 little graphs here. We're going to go one at a time. We're going to start at the top. These are words you now know, exergonic and endergonic. So exergonic means that we are releasing energy. Endergonic means that we are inputting energy. So let's look at an exergonic reaction on a graph with no enzyme present, and then we'll do it with an enzyme present. So on the y-axis is the amount of energy in the system. And then the x-axis is time. So how far along is the reaction? This is the end point of the reaction. This is the start point of the reaction. So when we look at this energy graph, we see that the energy of the system, remember, of the system, goes up, and then it drops way down below the starting point. So when we think about this in terms of Gibbs free energy, this hump right here, this hill, is energy, well, I guess the uphill part of this, so this slope, is energy being added to the system. That means I am taking energy and I'm putting it into this reaction. You know, this is called the activation energy, or EA. Activation energy, look at that, beautiful. So this is the activation energy. So even though this reaction is exergonic and it's going to release energy, to sort of get that release of energy going, I have to put in some energy, and that's the activation energy. But you can see, once I hit that threshold right here at this point, the energy starts leaving the system. The energy in the system goes down. Where's it going? Out of the system. We're releasing that energy. So this end point is lower than our start point. So the difference between the end point and the start point on any graph you see like this, that's your Gibbs free energy. That's just delta G. In this case, it's negative because it goes down. My end point is lower than my start point. So that's exergonic. Over here we have endergonic, which is going to be the opposite. You can see here that we start here and we end here. Right off the bat, you should be able to look at this and go, oh, that's an endergonic reaction. I had to put energy in, and I end with more energy in the system than I started with. Again, let me say that again. This delta G is positive because in the system, so within this molecule that I've built, I have had to put in more energy than I started with. The product is higher energy than the reactant, so I had to add energy to the reactant. This also has an activation energy, because you can see here after this point, there is a release of energy, right? Because our energy levels in the system go down a little bit, but not enough to compensate for all of this energy that I've had to put in. But that threshold right here, above that, is still activation energy. I'm still having to put energy in to activate it, right? So now that we've seen endergonic and exergonic without enzymes, let's see what happens with enzymes. So I'm just going to give it to you. EA, which is activation energy, is lessened. And remember, that's how I said enzymes work. They speed up reactions by lowering activation energy. So now this hump up here that was this much is just a little baby hump now. It's nothing. Notice, though, delta G is unaffected. Enzymes do not ever affect delta G. Never. The release of energy is going to be the same here, just like the input of energy that I had to do over here, net, is going to be the same. It just lowers the activation energy. It just means that this hill that I had to push and walk all the way up this hill to go down the hill, but now that's just a little baby hill. I can walk up that no problem. That's what enzymes do. Last page for chapter 8, it's going to be structure of enzymes, kind of. So this is the enzyme, and remember, an enzyme is a protein. So on this enzyme, you see this little cutout, looks like a square and then a triangle, and that's called the active site. And the active site of an enzyme is where the substrate, which is the thing the enzyme is going to affect, goes. And you can see that this substrate matches this active site. That is called specificity. And these two things together, when your enzyme and your substrate combine like a lock and a key, let's write that down. I like that. Lock and key, sure. Good Netflix series. Lock and key. The substrate is the key, and it fits specifically into the enzyme's lock, which is the active site. This forms the enzyme-substrate complex. And when these two things combine, the reaction can happen. We do the thing where we lower the activation energy and we speed up the reaction of whatever's happening. And it can also, it's worth knowing this substrate could be really anything, and this enzyme could look like anything. It could, substrates, it could be ATP, it could be ADP, it could be anything you want. Well, not anything you want. Anything you want in a biological system that exists. But just know that substrates bind to active sites of enzymes and form enzyme-substrate complexes. So now we're going to look at when enzymes stop working. So in this case, enzyme worked great, right? Let's talk about denaturation, temperature, or pH. So this enzyme is a protein. And if you remember proteins a little bit, we might have mentioned that proteins like to be at a very specific conditions. They like the temperature that they like, and they like the pH or level of acidity that they like. So if I raise the temperature a bunch, or let's say I drop the pH a bunch, this enzyme is going to deform a little bit. It's going to look a little weird. It might do something like that. It changes the shape, the temperature and the pH, and it could be a decrease too, or an increase in pH. Anything that is out of this enzyme's comfort zone in terms of temperature or pH can denature the enzyme. And when that enzyme gets denatured, it changes the shape of the active site. So now if we look at this active site and we look at this substrate, can I put that substrate there? Will this key fit into this deformed lock? No, it won't. So this enzyme is no longer going to function. So denaturation, temper pH, not going to work. Let's talk about competitive inhibition. Here we have an enzyme. He is happy. He's loving the temperature. It's a beautiful, let's say we're in the bloodstream and it's a lovely 97.8. Sure, I don't know. And it loves that. It loves that temperature. It loves the blood acidity. It's happy. And then there's this substrate. This looks good to me. This looks good. This could fit. But wait. Before this substrate is able to bind to this enzyme, this competitive inhibitor steals its place. It beats you to the chase. So now, this competitive inhibitor has taken up the active site. So now that active site is occupied. So can this substrate fit into this active site if there's something already there? No, it can't. So is this going to work? Is this reaction going to work? No way. No way, no how. These competitive inhibitors can be anything, though. This is, honestly, this is really important for medicine. You have a lot of medicines that competitively inhibit harmful enzymes. Well, not harmful enzymes, but enzymes that might be causing a problem. All right, last one, and then we are pretty much done with metabolism, is allosteric inhibition or allosteric activation. So here we have a substrate, and we have our happy enzyme. It's a triangle first, and then it's a square, like that. I know what I'm doing. So we have our happy enzyme. we have our active site, and we have our substrate, and it's ready to go. But you see this little notch right here? Let's say in this little notch, we have this guy, this molecule that fits into there well. Let's call this an allosteric site. We have this molecule, or this thing, that has bound to the allosteric site. And when it binds to this allosteric site, it can change this active site, but it could do one of two things. It could either activate this enzyme and make this substrate fit perfectly, or it could deactivate this enzyme, cause a conformational change, sort of round out this pocket, and then this substrate cannot fit. So if this allosteric site is activating the enzyme and saying, yeah, come on in, and we restore this triangle, then we would call this a coenzyme factor, which activates and makes it work. But maybe this molecule that binds to this allosteric site is a non-competitive inhibitor and inhibits. It just depends on the outcome. If we have something that binds to an allosteric site and that makes the enzyme do its thing, then it's a coenzyme factor. But if it binds there and shuts the enzyme off, then it is a non-competitive inhibitor. Last term I want you to know, we'll go more into this in cellular respiration, feedback inhibition. Too much product halts the pathway. So this is a specific type of inhibition. It could be competitive or allosteric inhibition or non-competitive inhibition, if you want to call it that. But feedback inhibition means that if we have done the pathway to heck, let's go, not that, let's go C6H12O6 plus 6O2 yields CO2, 6 of it, plus 6H2O plus a bunch of ATP. So we have this. If we have a bunch of glucose in our blood and it all breaks down, and then our ATP levels spike way the hell up, and we have a ton of ATP, it doesn't make sense for us to keep doing this. So we're going to inhibit this pathway. There are enzymes in glycolysis and Krebs cycle, very notably, that are going to be inhibited by high levels of ATP and stop doing cellular respiration. So that is it for enzymes. So it's a little bit longer than I wanted, but I hope this clears some things up. This is a really fundamental chapter. If you have any questions, please email me or see me on Tuesday at 8 a.m., which is an hour before your individual exam. Have a good one.